Hello, this is Professor Dan Kernler again, and this is our next video in our Calc 3 sequence. We are continuing today with Green's theorem and the green background. Today we're going to do the second version of Green's theorem. We talked previously about the circulation around the outside could be instead evaluated as a double integral of the curl inside. And so today we're going to talk about, or in this video we're going to talk about the flux. How much of the field is going outward across the path? And instead of doing that, we're going to do a double integral of something inside. So here we have Green's theorem. We should mention the requirements for Green's theorem that in order for it to apply, we haven't been specifying those maybe enough. So the region must be simply connected. The curve must be smooth. Right? The boundary of this must be a piecewise smooth. It can have little chunks to it, but no gaps. And it's oriented counterclockwise. Okay, so here is the second version of Green's theorem, the flux form. Here on the left, we have the flux, which if we go back to section 17.2, we had the circulation, which we talked about in the last video. And then on the bottom, we had the flux. How much of the field points outward is normal to the curve. Okay. So, and then we have the differential form. Again, this is the flux, but in differential form. And so now there's this other double integral here. You'll notice this is different. The partial derivative of f with respect to x added to the partial derivative of g with respect to y. Let's talk a little bit about what those might mean. This visual is a little less, it's not quite as easy to see like the rotation was in the previous one. We're going to try to show that if there's some kind of curve around this, that it will give a positive flux for this particular example. Of course, it won't always. So we need the partial derivative of f with respect to x. So f is going to be the x component of our vector. So we have x, and we need the partial derivative with respect to x. So we need to see what's happening to this as x increases. And we can see here, as x increases, f increases. So the partial derivative of f with respect to x is a positive number for this particular example that we did. And then we need to look at g and its derivative with respect to y. So we need to look at the y components of these vectors, and we can see that they are also increasing. Similarly, as y increases, g increases, the y component of the vectors. So the partial derivative of g with respect to y is also a positive number for this particular example. Taking those two forms, those two facts together, this means the partial derivative of f with respect to x plus the partial derivative of g with respect to y will be a positive number. And that implies then that the double integral of that over the region, whatever the region is inside this particular curve, would be positive. Let's see if we can visualize why that would be positive. The key is, if you look on, it seems like you've got left, it's kind of pointing inward, and right is pointing outward. But can you see that it has increased as we go across, so it's actually pointing outward more in the positive x direction. Similarly here on the y direction, there's some pointing in, and then there's some pointing out, so they might kind of cancel each other out, but they're in opposite directions. We have some going, sorry, they're not opposite directions. The one at the top, the one going out is larger than the one coming in. So there would be a net positive outward flux for this. And so what this is saying, this thing on the right, this double integral of the region inside, is actually a new quantity called the divergence. So the two-dimensional divergence of the vector field, and that's this partial derivative of f with respect to x plus the partial derivative of g with respect to y. But here's a little note, that divergence, if that divergence happens to be 0, we say that there's this vector field is source free on that region. So there's no net outward flux. Everything's going to stay inside that particular region. There's no net outward flow there. So here is, again, the second version. We have, let's scroll up and remind ourselves, the first version of Green's theorem. This is the circulation form, so the net circulation on the outside. You can instead do the double integral of the curl inside. And then now we have the flux form. If we want to know how much of like the net outward flux along the outer of the path, what we can instead is go inside and find the net outward divergence, the net divergence on that region, and those will be equivalent. So let's do some examples here. We have first one, a little bit of an application, and it's a little manufactured, but pretend we have a spring. Let me see if I can scroll down just enough to show the full example there. So we have a spring, and water is coming out from this spring, and we have a rectangle here. It's got the coordinates there, and we want to know, find the amount of water per second that flows across the rectangle. How much of the water flows across that rectangle? We could do this with a line integral. We could do it with the line integral. That outward flow, we could do the line integral, and this is closed line integral because it's a closed curve, of f dot product with n ds. And we would have to, unfortunately, we'd have to integrate over c1 plus the integral over c2 plus the integral over c3 plus the integral over c4. We have 4 different integrals we'd have to do there. What we're going to do instead is use Green's theorem and do a double integral over the region of the partial derivative of f with respect to x plus the partial derivative of g with respect to y. So let's see what that would be. Well, the region's easy enough here. This is just a rectangle. Y goes from, looks like -2 to 3. And then x goes from, that should be +3 there. And then x goes from -1 to 1. Okay, and then we need the partial derivative of f with respect to x. So there's our f. The partial derivative of f with respect to x will be 5. And then the partial derivative of g with respect to y will be 3. So it does not get much simpler than that. That's just the double integral of the constant 8. That's just the area of the rectangle times 8. So you can think about what that would be. But that's just going to be 8 times the area. So 8 times the area would be 8 times 2 times 5, and that's 80. The units here are weird. It feels like, 8 is like there's meters per second. Then we multiplied by the area, but if we didn't take time to derive what each unit was, but we would end up with square meters per second. You'd think volume, it's water, but we're just looking at it from the top. We would need the depth of those and multiplying by that depth. So this is really how much water is moving per square meter per second. Okay, next example, Green's theorem to compute the following. This is kind of an interesting one here. So we don't really have a curve, so let's make Green's theorem apply. We're going to assume it's a piecewise smooth boundary of some simply connected region, and we're going to compute it. So let's see what happens. 1/2 the integral, and we're going to have a closed integral now of this -y dx plus x dy. Well, let's pull this in so it looks like Green's theorem. -1/2 y dx plus 1/2 x dy. Okay, this must be our f, the partial derivative, or that's just f, yep, and this is g. This is the differential form of Green's theorem. Here we go. Looks like the signs are wrong, though. We have f dy minus g dx. Oh, yep, f dy minus g dx. So this is f. This is G, so they're kind of written in the wrong order there. Let's see here. So our Rolle's theorem says that should be the double integral over the region of the partial derivative of f with respect to x, that's 1/2, minus the partial derivative of g with respect to y, that's negative 1/2 dA. That's just the double integral of the region, 1 dA. That's just area. Well, that's kind of interesting. There's just a little trivia formula there. So this particular formula is actually the area of the region. So if we were to compute that line integral around the curve, we would get the area of the region inside of it. That's kind of cool. So make sure to make a note of that on your formula sheet. Okay, I believe we have a couple more examples. All right, let's use that theorem to find the area of an ellipse. This is one way to find the area of an ellipse. I don't really know that A is bigger than B here. That is not an ellipse, but we'll just pretend here. So A and B, and we're going to pretend we have an oriented curve that's oriented counterclockwise. And so what we're going to do is we are going to do the line integral y dx, or sorry, negative y dx plus x dy. If we're going to do the line integral, we need x and y in terms of t. And the way we can do that is kind of like a circle, where you have cosine t, sine t, but we need to stretch them a little bit, or maybe compress, depending on the values there. So we're going to scale the x to go out by a, and then the y is going to be scaled by b. And we'll go from 0 to 2 pi, and that will get us that ellipse. Okay, so let's take a look here. If x of t is a cosine t, then dx will be x prime of t dt, which will be negative a sine t dt. And similarly, if y of t is b sine t, then dy will be b cosine of t dt. Okay, so let's see, 1/2 integral of negative over our curve, negative y dx plus, what was it, x dy. That's 1/2 integral from 0 to 2 pi, negative, and y is b sine t, times, and then x prime of t is negative a sine t dt. And then plus x, which will be a cosine t, times dy, which is b cosine t dt. And you'll notice here we have 1/2 integral from 0 to 2 pi. We have ab sine squared t plus ab cosine squared t dt. So we can factor out an ab, 1/2 ab, integral from 0 to 2 pi. Well, that's just sine squared plus cosine squared, so that's 1 dt. Well, that's 1/2 ab t from 0 to 2 pi. Did you hear my cat? She wants to get out. All right, cat is out. That will be 1/2 ab times 2 pi minus 0, and so you get pi times a times b. Well, that's kind of cool. Area of an ellipse. The area of an ellipse is pi ab. Now the downside is you needed Calc 3 to be able to find that formula. I'm sure there are other ways, but that is the formula for the area of an ellipse. You can kind of compare that to the area of a circle, pi r squared, because the a and b are equal on a circle. All right, last example. This one seems is a little counterintuitive. It says use Green's theorem to evaluate the line integral Okay, it's fine, line integral. And this is actually a closed path here, where the field is x minus y and then 3y plus 5x, and c is pictured below. Now, you may be looking at that and thinking, well, hold on. Here's my region, but there's a hole in the middle. If we go back to Green's theorem, whichever version, it's the same, the conditions, it must be a simply connected region. It must be a simply connected region. So it doesn't seem like that's going to apply here. So here is how we kind of game the system. Let's start out here and let's move along our path. We're moving along. We're moving counterclockwise. Okay, that's good. Region's always on the left. Then I'm going to go down this path. I'm going to go turn left. Okay, region's always on the left. And then I'm going to come back out, and I went one way on that path, and I went the other way on that path. Those two line integral, think of the line integral, they would reverse each other. They would cancel each other out. And so I end up with this region, and because I sliced it down the middle, you could think of it unfolding, and it would be a simply connected region. So it seems to be kind of gaming the system. But there are ways to define a simply connected region, even though it might not look on the surface like it is simply connected. Okay, so now we can use Green's theorem, and we can find this line integral. And this is you see here, we're just going to find the line integral. So this is the curl version, the first version, go back to the beginning here. Sorry, scrolling fast. So this is the circulation version. This is not the flux version. All right, so that's going to be the double integral over the region of the curl, dA. And the curl was the partial derivative of g with respect to x minus the partial derivative of f with respect to y. And let's see here, that will be the double integral over the region. The partial derivative of g with respect to x will be 5, and the partial derivative of f with respect to y will be -1. 5 minus -1 dA. Okay, so that's the double integral over the region of 6 dA. And let's, again, because we have a circle, let's do polar coordinates. R, dr, d theta. R simply goes from 1 to 4, and theta goes from 0 to 2 pi. That'll just be, what will that be? 3r squared from 1 to 4 d theta. Four squared minus 1 squared. I could have done that in my head. That's 15 times 2 is 30. 30, then we'll get 30 theta from 0 to 2 pi. And so, wait, no, that's a 3. So 3 times 15 is 45. 45 theta from 0 to 2 pi will be 90 pi. The circulation there is 90 pi. Okay, and that is it for section 17.4, Green's theorem. Maybe we should finish the video, show my green screen in celebration of Green's theorem.